Okay, let's start chapter 19. Chapter 19 is related rates, and up until now, up until now, up until now, you know that y was a function of x. So for example, if we saw that y equals x cubed plus 4, and I asked you to take the derivative, you would say, fine, dy over dx equals 3x squared. But with related rates, the idea is that with related rates, the idea now is that y is a function of t and x is also a function of t. So the variables are no longer related to each other, they're related to t. And so for example, we're going to be talking about volume and surface area. So all those variables, you know, the volume, the height, the radius, all of those are functions of time. So if I ask you to find the derivative, the idea is we have dt of y is equal to d. If we want to take the derivative, the idea is that our variables are both functions of t, and it's like going back to implicit differentiation. We're not really sure what the function is, but we're going to take the derivative. So dt of y is dy t, because the derivative of y is 1, but we take the derivative of the function. And what's going on here is this is going to be 3x squared, right, because of chain rule, but and the derivative of 4 is 0, but we don't really know what x is, so we still have to take the derivative of x with respect to t. It looks a little, so it's interesting. Now, and the unit is called related rates. Now these rates are related in the way that x and y were related. Dy dt is related to dx dt. And so, you know, for example, what's going to happen is, the question is, they're going to give you all, it's another algebra problem. They're going to tell you the rate. So you're going to look for the word rate. And when you see the rate, it's either positive or negative. But the rate is, you know, dv dt, dr dt, dh dt. Positive or negative, and then they're going to give you a point at that specific time. So, for example, let's say, here's the example, you found the derivative, and they will say, if, you know, the rate of x is 5 meters per second, find the rate of y when x is 2. And so this is simply put, you're just substituting and solving an algebra equation. So you know that dy over dt is equal to 3 times 2 squared times 5. So let's see, what do we have here? 4 times 5 is 20, 20 times 3, it's 60 meters per second. So whatever's going on, so when x is changing, that makes sense. When x is changing at x equals 2, the rate is 60 meters per second. Okay, let's look at an example from the book. And the first example is example 21. Oh, is this chapter 20? Yes, it is. I'm sorry. This is 20a. So let's look at the first example from the book. This is example 28. I'm going to read, well, let me read it from the book. I have it worked out. It says, a spherical balloon is being inflated with air at a rate of 200 cubic centimeters per minute. At what rate is the radius increasing when the radius is 8 centimeters? So, a spherical balloon is being inflated. We know it's a question of volume. You get the formula for volume, but you should know. So the volume is equal to 4/3 pi r cubed. Now, in general, we say the volume is a function of radius, but here, volume and radius are functions of time. Let's review the question again. What information is given? So we know that, what are we told? we're told that dv over dt is equal to, 200 centimeters cubed per second. I'm going to leave the units off because I'm a little lazy, but I just want the number. So I know the rate of change is for the volume with respect to time is 200. What else are we told? We want to find dr dt. That's unknown, and we're told specifically at when the radius is 8 centimeters. Okay, so like the implicit differentiation, we're going to take the derivative of both sides with respect to time. So we have dv. We're taking the derivative of both sides with respect to time. The left side, well, the derivative of v is 1, but we still have to take the derivative of that thing inside. So it's dv dt. What's going on inside? Well, what's the derivative of 4/3 pi r cubed? It's 4 pi r squared, but then the chain rule says we have to take the derivative of the r function. We don't know what that r is. It's a function of x. So it's dr dt. And so we have our three variables. We have our two rates and our radius. We know dv dt is 200. We don't know what the rate of change is for r, but we're looking for when the rate is 8. So it's 4 pi 8 squared dr dt. Once again, dr dt is our unknown. So we know we have, 64 times 4 is 256. So dr over dt is 200 divided by 256 pi, which is approximately 0.249. 0.249 watts. What's the rate of the radius? Centimeters per second. Or minute. I'm sorry, second. Okay. Let's look at the next example from the book. I'm erasing. The next example from the book talks about an icicle cone. Why don't you look at the question, get to the question, and I'll read it out loud. The question is, as a conical icicle melts, the rate of decrease of height h is 1 centimeters per second per hour, so they left off the hour, and the rate of decrease of the radius of the base r is 1/10 centimeters per hour. At what rate is the volume of the icicle decreasing when the height is 30 and the base radius is 4? Okay, so we know we have it's the whole thing. So it's the volume, and it's a cone. So we know from the formula that's 1/3, right? We know that we learned in geometry that the volume of a cone is 1/3 the volume of a cylinder, and we know the volume of the cylinder is pi r squared height, because I think I described that as a bunch of pancakes on top of each other, but the cone is 1/3 of that. Now, I'm going to write it, what the book does is they kind of write it separately. So they're going to write like two functions here. So 1/3 r squared is like one function, and the height is another function. Remember, volume, radius, and height are now all functions of time. Also, what we see here is we have two functions then. So when we take the derivative with respect to t, it's going to be like the product rule. Very basic. So, once again, I'm taking the derivative with respect to t. So on the left, I have dv over dt. On the right, let's see, I'm going to take the derivative of the first, keep the second, and then keep the first, derivative of the second. What did I say? Derivative of the first, keep the second, plus keep the first, derivative of the second. Okay, derivative of the first, 2/3 pi r dr dt h plus 1/3 pi r squared dh dt. Okay, well, we have a lot of variables here, but So does the question give us all, are one of these is missing? So let's look again. Let's see what they tell us. So they're telling us that the height decreases at a rate. So we have dh dt is -1. I'm going to leave off the units. It'll make your life easier. What's going on with the radius? The radius is decreasing at 1/10. Remember that? Negative. What other information? At what rate is the volume decreasing? So we don't know dv dt. That's unknown. So my question better give me this r and this h. Well, oh look, it gives it. What happens at the moment when the height is 30 and the base is 4? Height is 30 and the radius of the base is 4. We have all the information. We're just missing this last piece of information. Plug it, get the derivative, plug the information in. Obviously, this is going to be a part 2 question. Let's see, r dr dt, -0.1, the height at 30 plus 1/3 pi 4 squared dh dt, -1. Final answer, once again, this goes in the calculator. You get negative, what is it? Yeah, it goes in the calculator, -41.9. And what's the units? It's the volume, right? So it's centimeters cubed. The volume is changing. Centimeters cubed per hour. Yeah, so work on the problems in the book. So the idea is, so work on the problems I assigned you, and then I give you some extra problems.